Thank you, Ajad. Welcome to session 7. So, let me share my screen. So, as I mentioned in the website, today we will talk about a hydraulic jump. What is a hydraulic jump, and what is the practical applications of this hydraulic jump, and how we can solve questions related to hydraulic jump in a gate. So in this session, what we do is that first we will introduce the hydraulic jump definition and the application of hydraulic jump. And we'll see the formulas and types of jumps. And after that, we'll solve recent questions from GATE 2022 related to hydraulic jump as well as profiles, flow profiles. So total three questions we'll solve in this session. So I'll try to make it like more simple and simple to understand while solving the question. So yeah, let's proceed further. Okay. Uh, let me on the presentation mode. So, is the slides visible? Can anybody respond? Hello. Thank you. Okay. So let's proceed further. So what is the hydraulic jump like? Let's say how we can see there are multiple definitions, but I have taken the broader one here. So suppose let's say there is a like a channel like this. Assume this is a bed of the channel. So and this is a horizontal surface. This is a horizontal channel. So when there is a situation like this, so water will move at a uniform flow. Assuming that the channel is a prismatic, let's say if there is an hump or maybe a drop, maybe a drop or maybe a weir type of structure. When the flow or takes place over these kind of formations, so the flow properties alter. The flow properties may alter. Either velocity may alter or depth may alter, or as well as the specific energy and specific force. All these thing flow properties will change as when the water what flow takes place over these kind of formations. Okay, so this is a general case. So, but when we call like let's say if the water is flowing over the sump, can we say it is a hydraulic jump? Either can we say like when the flow takes place over this kind of drop, can we say this is a hydraulic jump? No. So to make it clear, there is a general definition to it. So the rise in water level which occurs when the liquid at high velocity discharge into a zone of lower velocity is called hydraulic jump. So in the hydraulic jump, what typically happens is that let's say this is like assume this is channel bed. So you install some sluice gate here, okay, and this is upstream side and this is the downstream side. Okay, when this is a case, so let's say when you push the sluice gate down, so what will happen? The flow tend to rush tend to rush after certain distance from the gate in a downstream side. The depth will increase. The depth will increase. Why? Because like, when you applied a actional force like a sluice gate in the flow direction, and the flow is changing from high depth to low depth. Here it's a maybe a y1, here it is a y2. Okay, so here y1 is greater than y2. Okay, and when you applied a sluice gate here, the f- we are pushing the water to, we are making the water to rush. So when the water is rushed towards this in this narrow region, here the velocity, the depth is small, then velocity will be more. So here the flow condition can be considered as a supercritical flow. Okay, after certain distance from the sluice gate, the flow will lose its energy continuously due to the friction. After certain distance, it the velocity will reduce and a small raise in the water level will takes place. And this kind of structure, this kind of formation is called hydraulic jump. Okay, this is called hydraulic jump. So it's nothing but when the flow, the raise in the water, like here, see what why we are doing in hydraulic jump, like we are artificially increasing the depth of water level in the channel. So how we do? So we create a zone where is a high velocity zone, and this high velocity zone will lose its energy as it flows towards the downstream. As soon as after certain distance, it loses its energy and it forms a jump. Okay, so a rise in the water level which occurs when the liquid at a high velocity discharge into a zone of lower velocity is called hydraulic jump. See, the hydraulic jump dissipates the surplus energy of water. So one of the application is that dissipates the surplus energy of water. Suppose let's say you have seen in the dams or anywhere, when they open the gates, the water rushes towards the downstream. So but at the if you clearly observe, let's say this is the dam, this is a dam, and so let's say if the water is reached above this dam level, now when the water is flowing over this dam, it will rush at a high velocity. We will be much higher. Okay, but at the downstream, what we do is that we create a some kind of a, we create a kind of a spillway structure. So this whole structure is called a spillway. But what we do is that at the downstream, we'll create this kind of a formation such that the water energy, we will dissipate the kinetic energy available with the water. So in this case, by doing this, so we will reduce the erosion at the downstream, as well as we will maintain the, we can maintain the water depth at the downstream. So this has a several applications. We'll see what is that. So first is that to dissipate the energy in the water flowing over the dams, we are our hydraulic structure that prevent scoring. As I mentioned that by reducing the velocity, we can prevent the scouring, as well as the erosion in the downstream of the structure. As well as sometimes in irrigation channels and in other channels, sometimes the head means the outlet of the irrigation canal may be little higher than the bed. So in that case, if the depth of water is not available, so what we do is that we purposefully create a hydraulic jump to recover the head or rise of the water level on the downstream of the measuring flume, thus maintain the hydraulic level in a channel for irrigation. So suppose let's say this is a channel, you have this depth up to here, but you have the outlet here, which sends the water to irrigation. Okay, so but so now we don't have extra water here. What we can do is that we can create a hydraulic jump at upstream section, such that water level in this downstream section can reach to this outlet. So in this way, we can so the here the velocity can be smaller, and the discharge can be uh, less, but still we'll recover the head, and we supply the water to the irrigation. Okay, so this is another second application. And the third application is that to increase the weight on the apron. I think most of you know what is an apron. This is a structure built at the downstream of the weir or dams. Okay, and thus reduce the uplift pressure under the masonry structure by raising the water depth of the aquifer. So let me draw this figure, so maybe it will be clear for you. So many of you might have seen in irrigation engineering. Okay, let's say this is a weir. Let's say water is flowing over this particular place. Okay, water is flowing in this manner. So but as we know, there is a seepage also. There is a seepage also. Because of this seepage, there will be an uplift pressure of apron. So to maintain, to retain this uplift of the structure, what we need to do, we need to maintain this depth of water, weight of water, such that we can reduce the uplift pressure. Okay. And another application is that to mix the chemicals used for the water purification. Okay, when this jump happens, there will be a lot of turbidity takes place in this jump. So this will be effectively used to mix the chemicals for water purification. As well as in this process, we can even aerate the water for city water supplies, and we can remove the air pockets for the water supply. So these are the few applications related for the hydraulic jump. Okay, let's see what is a hydraulic jump, like how we can represent, like schematically. So here we can see this is a, this line, this is a hydraulic jump. This is a hydraulic, follow this red line. This is a flow surface. So here you can see this arrows, curved arrows shows the turbulence. Okay. So here if you clearly observe, there are two depths mentioned. One is a sequence depth, one is alternative depth. So in session 3 I have mentioned what is the difference between alternative depths and the sequence depths. So in alternative depths, y, here you see the notation, it is showing it y2 dash and y1. So these are alternative depths. They both will have a same specific energy. Okay, and sequence depths. So this is one of the important question in a gate for 1 mark. So kindly note down this point. So this is like y2 and y1. These both will have a same specific force. So many times this question is asked, like not only in the gate, even in the SSC, JEE and other state exams also. This is the most important question. Like the sequence depths will have a same specific force, whereas alternative depths will have a same specific energy. Okay. So that is a point. And this is, and the curve drawn between the specific force and the depth is called a specific force curve. Okay. The curve drawn between the specific energy E1 or E bit under the depth is called a specific energy curve. So this is also one of the important. So what is the specific energy curve? A curve between specific energy and depth. Okay. And specific force curve between specific force and depth of the flow. So these are the, like in this slide only you can expect more question, more like you can note it on the most important questions. One is that alternative depths, like what is the difference between alternative depths and which is a constant between for the alternative depths. So for alternative depths, y2 dash, like it will have same specific energy, whereas sequence depth will have a same specific force. A curve drawn between the specific energy and the depth is called specific energy curve. A curve drawn between this specific force and depth is called specific energy force. These are the basic terms. Let's look at the hydraulic jump first. So here the section 1, here is the section 1. It is called a section before the jump. Before jump. So the section 2 is after the jump. So here jump is nothing but the rise in the water level. So here the jump is nothing but the rise in the water level. So here this is a high velocity region and this is a low velocity region. So when the water is allowed to move from the high velocity zone to the low velocity zone, the rise in the water level takes place, and this particular phenomenon is called hydraulic jump. Okay. And here here at the before the jump we have shown what is the specific energy E1, and after the jump also we have shown what is the specific energy E2, and there is an energy dissipation delta E. So the delta E can approximately equal to as much as equal to even also. We can create a jump in such a way that we can dissipate all the energy available with water also. So that is a level we can do. Okay, these are the basics about the few basics about the hydraulic jump. Yeah, one more point I would like to mention here. See, if you follow this dashed line, this is the initial depth. So this dashed line, red line, this is the initial depth, which is y1. And if you follow this line, like after at section 2, if you mark at this point, and the depth corresponding, this is called depth after the jump. So here y1 is depth before jump, and y2 is depth after the jump. So can anybody say what is the Froude's formula here? Like so suppose, let's say, how we can calculate the Froude's. Suppose similar, like suppose fr1, here fr1 and fr2 are Froude numbers of the flow before and after the jump. See, this is like in the questions we will use the Froude number exclusively to solve all the questions. Froude numbers before and after jump. Okay, so I hope all of you know what is the Froude number. Froude number is fr equal to v upon root over gy for rectangular channel. For rectangular channel, for a general case, it will be like fr square equal to q square t divided by ga cube. Okay, these are the general equation, and above v upon root over g by b is for the rectangular channel. So these are the few basics. Let's see what are the type of jumps. Suppose based on the Froude number before the jump, f1, here f1 denotes the Froude's number before the jump. So we will follow the same notation. Froude number before jump. So f2 will be Froude number after jump. Okay, so let's say based on the Froude number before the jumps are classified as 5 jumps. Total 5 types. Okay, so sometimes it may be useful to ask, like some you can expect one more question for like a study jump. What is a Froude number? The study jump is important one. Study jump is an important one. Okay, so if you see, this is an angular jump, and which has a range. Froude number ranges between 1 to 1.7. So as we know, like when fr greater than 1 is called a supercritical, so less than 1 is called subcritical. Okay, I think all of you know this thing. So let's say when this Froude number between 1 to 1.7, the Froude number before the jump. So before the jump, let's say this is section 1. So here if you calculate the Froude number fr1, f1 or f1, if the values lies between the 1 to 1.7, we can get only the angular jump. Okay, we can get only the angular jump, like which is not a significant jump. So if you see, after certain distance, the depth is the rise in the water level is again decreasing. So but it may not serve our purpose. Our purpose is to recover the head or raise in the water level in the downstream. Okay, and if you see the weak jump, in the weak jump, the change in the depth may be a smaller. Okay, and when this happens, when the Froude number between 1.7 to 2.5. So these values also very important. You must remember the values. So this is an oscillating jump. So the jump won't be the steady. It will oscillate along the downstream. See, along the downstream, and it propagates towards the down, like the oscillation propagates towards the downstream. So and this is not good for the channel lining. So if the oscillating jump it takes place, these kind of oscillations may damage the channel lining. So okay, so f1 is this oscillating jumps takes place when Froude number is 2.5 to 4.5. These numbers are important for IAS exam, not for the gate. You may not you may not ask to remember the exams, but values. But in IAS, you can expect these numbers. One more questions are based on these fraud numbers. So which type of what is a fraud number range for the study jump, what is a fraud number range for the strong jump, like that. So when the fraud number is between 4.5 to 9, we can expect the study jump. When the fraud number is greater than 9, this is a strong jump. Okay, so you can remember in such a way, like 1 to 1.7, 1.7 to 2.5, 2.5 to 4.5, 4.5 to 9.0, and greater than 9.0. Okay, so how you can remember? Angular jump. Okay, weak jump and oscillating jump, and as well as strong jump. Sorry, steady jump. Sorry, steady jump and strong jump. So we must remember these five types of jumps. Okay, so this is about the types of jumps. Let's see the basic characteristics of the jump. So these are the few these are the important equations for solving the equations. So if you remember these three equations, 99% you will able to solve the questions from the hydraulic jump. The first equation is the relation between the depths to the Froude's number at the before the jump. So here F1 is a Froude number before the jump. Okay, before the jump. Suppose if you draw line between y2 divided by y1 to the Froude number 1, it follows the straight line, and this particular equation is the equation of this particular line. Okay, 1 by 2 root over 1 plus 8 f1 square minus 1. This is the equation for this particular line. Okay, so you can remember this thing, y2 minus y2 divided by y1 equal to 1 by 2 square root of 1 minus 8 f1 square minus 1. Okay, this is the important equation. Similarly, one can write this also, y1 divided by y2 equal to 1 by 2 root over 1 plus 8 f2 square. Okay, this is also possible. So these are the one, if you remember, this equation is pretty simple to write this another equation. And okay, and this is another term. As we have seen in this slide, there is energy loss takes place when there is a hydraulic, when water is raised, when the hydraulic jump has placed. So that how we can calculate that energy loss? So the energy loss in the jump is equal to specific energy before and after the jump. So it can be shown that the loss is by using this particular formula. So what is the so these derivations are not necessary now, so you can remember the formula directly. So the loss of energy in the jump is equal to the difference in the specific energy before the jump and after the jump, which is equal to y2 minus y1 whole cube divided by 1 4 into y1 y2. And what is the height of the jump? So the difference between the depths after and before the jump is height of the jump. So here the jumps we talked in terms of the relative depths with respect to the specific energy at 1. Specific energy to. So if you these are the three equations to be remembered. So what is the first equation? Relation between the depth. So y2 divided by y1 equal to 1 by 2 bracket open square root of 1 plus 8 f1 square minus 1. This is the first equation to remember. The second equation, delta E equal to y2 minus y1 whole cube 4 y1 y2. Third equation, hj divided by e. So one can even cancel this e1 from the both the sides. You can simply write y2 minus y1 also. This is also possible. Okay, this is called height of the jump. If you remember these three equations, 99% you will be able to solve the questions from hydraulic jump. Let's see the question, because which I have taken this question from gate 2022. This is gate 2022 set to question. So Many of you might have attempted this question in the exam. Let's see how we can solve this question. So this question can be solved using two approaches, and surprisingly these two approaches leading to the different answer. But for the evaluation, they have given the broad range, and the two both the approaches are answers are falling in that range only. So we'll solve this question by using both approaches. So you can feel free to adapt one of the approaches, one of the approach. Okay, so the question is as follows: the hydraulic jump takes place in a 6-meter wide rectangular channel at a point where upstream depth is 0.5 meters. So it can be denoted as y1, which means depth before the jump, or even they mentioned in the question also just before the jump. If the discharge in the channel is 30 meter cube per second, and the energy loss, so energy loss is delta E, and the discharge is Q, then the fraud number computed at the end of the jump. Okay, so what is the question they asked? F2. So they are asked to calculate the F2. What is F2? F2 means depth fraud number after the jump. Let's say if I draw this figure, hydraulic jump figure. Let's say this is okay, this is section 2. Let's say this is a section 1. Okay, and now they have given us this as 0.5 meter, and this is y2. Okay, okay, and parallelly they have given 6 meter, 0.5, yet 1 1. Okay, these are the given data. So what else they have given? Q equal to 30 meter cube per second, and G assumed to be 10 meter per second square. Okay, and yes, delta E, energy loss. Suppose here if you calculate, the energy will be E1, here it will be E2, and the difference between E1 and E2 is given as 1.6 meter. So I'm giving you 1 minute. Can you just try calculate by using this thing. So I have shown you this equation, the three equations. So it will be useful to solve the question. So either you can take first equation and second equation. Both the equation will give the answer. Okay. Let me interact with you now. So can anybody guess the answer? How much is the answer? Hello. Okay. Anyway, we'll see the solution in the next slide. Okay. Let me go to the screen share this mode. Okay. So as so we have taken this first relation, which is like a depth y2 by y1. So we will there are two approaches I mentioned. This is approach 1, this is approach 1, by using y2 by y1 equal to 1 by 2 square root of 1 plus 8 f1 square minus 1. Okay, this is approach 1. So we will use this particular formula and we'll solve the question. So what are the given data? One is width of the channel given as 6 meter, and discharge is Q as given as a 30 meter cube per second, and depth before the jump y1, which is equal to 0.5 meter, and acceleration due to gravity is 10 meter per second square, and energy loss. So for the approach 1, we don't need this energy loss. This is a redundant data for us. So let's see. So as we know, what is the Froude number for rectangular channel? Froude number is f1 equal to v1 divided by root over gy1. Okay, so I have shown in the previous slide fr equal to, for a rectangular channel, gy, or for this is for exclusive for rectangular channel. For general case, it will be like Fr equal to, so q square t by g a cube square root of, okay, sorry, this is a for a general case, for general case. So fine, but in most of our examples are related to rectangle, so no need to remember this q square t by g a cube, but it is good if you remember this formula. But this is the most relevant formula for us, v upon root over g into y. Okay, so what we do is that first we'll calculate the forward number at upstream section. For to calculate the forward number at the downstream section is the required answer. So for to get that, we need to know what is the depth at the depth after the jump as well as the velocity after the jump. To arrive this particular quantities, we will use this relation y2 divided by y1, which is equal to 1 by 2 in 1 by 2 square root of 1 plus 8 f1 square minus 1. So we will use this particular relation and we'll calculate. In this relation, what all we know? We know y1, which is given as 0.5 meter, and f1 square, which can be calculated by using this particular formula. Okay, and so only unknown is y2. So that is straightforward answer. So what is the velocity? As we know, q equal to a into v. So for rectangular channel, A equal to B into Y. Okay. So here we know the B and even know the Y. So B is a 6 meter they have given and Y is 0.5 meter. So because we are calculating the section at 1. So it will be like V1. So 30 meter cube per second divided by 6 meter into 0.5 meter, which gives us a value of 10 meter per second. That is a V1. So now let's use this particular V1 to calculate the F1. So F1 equal to 10 meter per second divided by square root of, here the 10 is acceleration due to gravity. So meter per second square, and this is meter. Okay. So the 10 into 0.5, square root of 10 into 0.5, this will give us a value of 0.472. This is a fraud number before the jump. Now let's use this particular value and substitute in this equation. So y2 divided by y1 equal to 1 by 2 square root of 1 plus 8 into 4.472 whole square minus 1. So which gives us a value of 5.844. Now we know the y1 from this relation and we can directly calculate as y2 equal to 5.844 into zero point 0.5, which gives a value of 2.992 meters. Okay. Now what we know? So to calculate this f2, we know we got the value of y2 from this relation. Now our aim is to calculate this v2. So what is how we can calculate the v2? Again, v2 equal to, this is a discharge and this is a width will be same, even the before the jump and after them the width will be same, only the depth will change, y2. So we can substitute as bq divided by b into y2. So by doing that we can get the velocity. If you clearly observe, the velocity before the jump is around 10 meter per second, but the velocity after the jump, if you see, it is 1.77 meter per second. Even similarly, the depth before the jump is given as 0.5 meter. When we compute the depth after the jump, we got around 3 nearly 3 meters. Okay, so you see the rise in the water level. Okay, now by using this v2 and y2, we can calculate the f2. So f2 equal to 1.77 divided by square root of 10 into 2.992, which is nothing but 0.316. But in the question they told to round it up to two decimals. So it will be like 0.136 approximately equal to 0.32. So in the exam, the range was given as 0.3 to 0.41. So our value is far lied between this range. Now let's look at the second approach. See, this is a 2 marks question, just a substitution. Just a substitution gives us a 2 marks. If one remember this particular equation, this is easy to get 2 marks in this area. Okay, this is alternative solution or approach 2. Okay, approach 2. So in this approach, what we do is that we will use the we will use the energy loss information which is given to us. So as we know, delta E equal to E1 minus E2, which is equal to Y2 minus Y1 whole cube divided by 4 into Y1 Y2. So now what we know this formula from the previous slides. Okay. So y1 y2 minus y1 whole cube equal divided by 4y1 y2. So now substitute the values. As we know, delta E is given as 1.6 kilometer. This is the given data. And y2 and y1 we know this is also given in the question, 0.5 meters depth before the jump. And so we substitute this equation. Okay, 1.6 into 4 into point. So now let's shuffle the term so you can bring it here. So 1.6 into 4 into zero point 0.5 into y2, which is equal to y2 minus 0.5 cube. Okay, so this is in the form of a minus b whole cube. So how we can expand, which is equal to a cube minus b cube minus 3a square 3ab square. If one has a confusion to expand this thing, you can written as this thing, a minus b into a minus b whole square. This a minus b is easy to a minus b whole square is easy to remember, so we know. So a minus b can be written as a minus b a square plus b square minus 3ab. If one expand this thing, we will reach to this particular equation. So we did the similar manner here. So a cube minus b cube, okay, uh, minus 3ab square plus, sorry, 3a square b plus 3ab square, and this is a extra term we have in the other side, so we brought it back, brought to the right side, left side, and made it equal to 0. And this particular equation is difficult to solve with hand, so one can use a calculator, and by or there is a methodology to estimate the roots also. So if we estimate the roots, we have got three roots. One is to satisfy this particular equation, we got the three roots. One is 2.5 meter, another is 0.0527, another is 0.0947. But depth cannot be negative, so we can neglect these two. So final depth can be 2.5 meter. So use this particular information to calculate the v2, which is equal to 30 meter cube per second divided by 6 meter into 2.5 meter. 2.5 is the depth after the jump, and this is a width, 6 meters of width b, and this is a q. So as we know, q equal to a into v. So we are doing the simple that form, we are using that formula only. So v2 equal to q divided by b into y2, which gives us the value of 2 meter per second. So how much we got before? We got before is 1.77 meter per second, but with help of approach 2, we have reached to the value of 2 meter per second. Okay, that there is a slight difference in the values between the approach 1 and approach 2. So but don't worry, the range, the correct value range, they have given us 0.3 to 0.41. So this alternative solution also will fall in this range only. So okay, now we know v2, and how we can calculate f2? F2 equal to v2 divided by square root of g into y2. So as we know, y2 equal to 2.5 meters. So by substituting this thing, we reach to the value of zero point 0.4. So in the previous approach, we got a value of 0.232. Here we got a zero point 0.4. Both the approaches are correct. Both the approaches are given full marks. So don't worry. But one point I would like to emphasize here is that just remember, by remembering three equations, these three equations, you will able to score 2 marks. Suppose if any question comes from the hydraulic jump, it is a simple marks to put it in a pocket. So just remember these two equations, your job is simple. Okay, that's it about this hydraulic jump. So there are a few other questions, but the model is same. So the values will be changed, and in the broad sense, this is a model you can expect in the gate exam. And for IES also, I have mentioned what are the questions can be asked, like for example, types of jumps, and fraud numbers for the each jump, corresponding to each jump. So if you remember these few points, that is enough for the competitive exams. Let's solve one more questions from the gate 2022. So it appeared in gate 22 set 2. The question number is 20. Okay. Okay, so I'll just give a 1 minute. Can anybody say what is the dimension of a dynamic viscosity here? And dynamic viscosity represents with the symbol of mu. So can anybody just guess it? Like maybe it can be wrong, but you can guess it. What is the dimension of dynamic viscosity? Even this
First
particular,
option, sir.
correct, correct, very good. So this particular approach we discussed in the session 4. Let's see what we do in the in the dimensionality analysis. uh, we How we shown the units. So for mass, which has a units of kg, we shown with a symbol of m. Okay, or for length or a distance or a width, any measurement which has units of meters, we shown with the symbol of l. And the the unit which is time, which is a seconds, we shown with the symbol of t. Okay, so let's take few examples, like, so how we can say acceleration in terms of this MLT format. So acceleration is nothing but velocity upon time. Okay, what is velocity? Velocity is length or sorry, slash a displacement per time. Okay, divided by time. Okay, now how we can solve? So let's say length or displacement we represent with the we represent, we shown with the symbol of l. Okay, l by t divided by t. So how we can show l by t, t square? So it can be written as l t minus 2. In the similar manner, we can represent all the unit all the symbols in a MLT format. This is a this particular procedure, I have explained in the dimensional analysis, but you can still revise that session 4, and that link for that particular session will be uploaded in the website. You can follow the website to look the session 4. Okay, so the SI, so these are MLT formats we use for the SI system. Okay, the SI physical unit of dynamic viscosity mu is a Pascal second, which is identically equal to 1 kg per meter per second. So kg per meter per second. This is a units of dynamic viscosity. Units of dynamic kg per. So what is the kg? How we can represent? We can show with kg. Kg will show with the symbol of m, and meters will show with the symbol of L, and seconds LT. So which narrow down to M L power minus 1 T power minus 1. So option 1 is correct answer. Thank you. Okay. Okay. So this is a one tricky question. This is from again Gates 2022 set 2. Okay, question number 47. This particular question has multiple answers rather than the single answer. So kindly read this question and just guess it, like what are the correct options here. So this is related to the critical flow. Uh, this is critical related to the critical flow. Just guess it, like how we can solve this. What are the options? So let me read the question for you. Water is flowing in a horizontal, frictionless, rectangular channel. Okay, a smooth hump is built. So let's say assume this is a channel. This is a channel bed. Okay, and a hump is built which has a height of delta z. Okay, fine. And it height gradually increase to reach to, so sorry, this is not a sudden, so they have built it in such a way like a sudden increase. Okay, so this is a way they constructed. So the height is gradually increased to reach a choked condition. Kindly remember the choked condition. The choked condition means delta z is equal to delta z max. Okay, I'll tell you what is the delta z max. Okay, the depth of water at this section y2, and that is upstream section is y1. Suppose let's say if the flow is taking place over this particular section, this is y1, and this can be either in this case, or like based on the flow condition it will change. Let's say for the sake of this is y2, this is y1. So now the correct statement or statements for the choked or unchoked condition in the channel are. So this is a scenario. Now just guess it, what are the options are what options are correct here. The first option is In a choked condition, Y1 decreases if the flow is supercritical and increases if the flow is subcritical. Okay, let me tell you what is choked flow. Okay, suppose suppose I think this I have shown you. This is a specific energy curve. This is specific energy curve, and this is a graph curve between discharge and the depth. Okay, discharge and depth. Okay, so as all of you know, this is a specific energy curve, and this is a minimum specific energy required to take the to take the flow required to flow takes place. Okay, and this particular this curve has two sections. One is subcritical and the supercritical. Okay, let's say draw one vertical line like this. Let's say this we mention as E1. Let's say for example here, let's take the same question. This is a channel bed. Now construct a ramp. Okay, this is a ramp. This is a delta Z max. Okay, so at some distance it will be same. It will be delta Z only. Let's say this is a section 1, and maybe let's say this is a section 2 where Z equal to Z max. Let's say if I calculate, this is E1 and this is E2. So as according to specific energy principle, E1 equal to E2 plus delta Z max or Z if we go into the second section 2. Okay, so suppose let's say if we draw a line correspond to value of E1, this is E1 and this is E2. Okay, okay, this is E2, and correspondingly we will have one depth. Correspondingly we will have depths. Let's say this is a Y1 Y1, this is Y2 Y1, this is Y1 2, and this is Y2 dash. Okay, so as you know, all of you know, this for the same specific energy we have alternative depths. Okay, let me read the options first. Okay, oh, there's one term here, hooked announce. Okay, this is the case. Okay, so as you increasing the height of this hump, okay, as you increase the height of the hump, this particular line moves towards this critical energy position. So after certain height, after certain raise in the hump, let's say when we reach to the Z max, the energy available at this particular flow is E minimum. Suppose if we raise this particular bed even further, the the discharge won't be the same. If you see, this is for a constant Q, and the discharge won't be the same, and the specific energy curve will shift. Either it will shift towards right, it will shift towards right. This will become E minimum. Okay, to maintain this, to maintain the discharge. Okay, so that particular condition is called choke flow. Choke flow happens when the transaction, the depth is more than the Z max, such that the specific energy for a given constant Q is not available. During that case, the flow condition is called as a choke flow. Okay, now read the options. Let's see, let's look at the option C. Okay, in unchoked condition means this curve will be valid, this blue color curve will be valid, the blue color curve will be valid. So this is a for the same constant Q. For a choked condition, this Q will become Q dash. Okay, in the choked condition, the discharge will change. In unchoked condition, The y1 remains unaffected when the flow is supercritical or subcritical. Okay. Suppose let's say this is a y1. Suppose let's say you raise this hump to some delta z. Okay. This is a flow at y1. Now let's say the flow is subcritical. What will happen? The discharge will reduce and the depth will decrease. Okay. And suppose if the flow is supercritical, the depth will increase like this. So it does not alter the upstream depth. So option C is correct. So in unchoked condition, Y1 remains unaffected when the flow is supercritical or subcritical. Okay. In a choked condition, what happens? Like, let me put it in the correct words. In a choked condition, for the flow to be possible, okay, for the choked condition, the upstream flow condition must change. Okay, in the choked condition, let me write it in here so that it will be clear for you. In choked condition, the upstream flow condition must change. Okay, that is the E1 is the initial one, and from E1 it will increase to E1 dash. So in this condition, the depth will change. Okay, and such a way that E2 will become equal to E minimum. Okay, E2 will become equal to E minimum. What I mean here, let's say this is a specific energy curve. This is a curve, initial curve. Sorry, asymptotic. This is the initial curve, one situation. Now let's say if the choked flow happen, the curve will shift towards right. Okay, and this is let's say E minimum, and this is E2. Now the curve will shift in such a way that the E2 will be equal to E minimum, and this is E1, and this will go to E dash 1. This is E1. Maybe this is slightly confusing for you. Don't worry, you will get to it. It's a simple, straightforward only. Okay. This is initial. This is a secondary. Okay. This is for a choked condition. Okay. So let's say this is a two regions, super and sub. So let's read the first option. In choked condition, Y1 decreases if the flow is supercritical. Okay. Please bear with my drawings. This is super. This is sub. This is E1. This is E1 dash as I mentioned. Now let's say, so this is like in this manner, not sorry for this thing. This will increase in this way. So the y1 decreases if the flow is supercritical and increases if the flow is correct. Suppose as E1 is shifted to E1 dash, the depth again is further decreases. If you correctly remember, this curve will be asymptotic to x axis, so the depth will decrease. Whereas in supercritical, the depth will increase. Okay, the depth will be increased for the same. So let's say here it will be here, but for the even the depth is here. So option 1 also correct. For in a choked condition, y2 is equal to critical depth if the flow is supercritical and subcritical. Thus I have mentioned in the choked condition, your upstream flow condition must change such that E1 equal to become E1 dash and E2 become E minimum, and correspond E minimum is a critical state of flow. Okay, so option or this option also correct. So now so far we have shown that three options are correct. What is the third option? Fourth option, in a choked condition, Y1 increases if the flow is supercritical. This is wrong. Okay, this is wrong. So correct answer options are A, comma B, comma C. Okay, so see, this is very simple if you know this particular diagram only. If you know the specific energy curve. So specific energy curve, like see, when you increase the hump after certain distance, like more than Z max, then the curve will shift to the right. Just plot the curve and you can able to interpret all the results. See, in the similar type of questions you can expect in IES a lot than the gate is like very few. Once in a 3 years, once in a 4 years you can expect this type of question, but in IES this is a confirmed question you can expect, like for at least for 1 mark or 2 marks. Okay, you must remember use of the specific energy curve. So it's already 6 o'clock. Maybe I can wind up here. So yeah, for the last question, it's not only the one option, like three options are correct. A, B, C, all three options are correct. So somebody told only B, but all three options are correct. So thanks for joining this session. In the next session, we will talk about the written periods and written levels. Okay. So that's all for today. If you have any questions, you can ask me. Otherwise, you can leave the meeting.